Welcome to the Brain and Space. I'm Jennifer Groh, and I'm a neuroscientist at Duke University. This class is all about how we figure out where things are, things that are out there in the world, and where we are with respect to that world. In this class, you'll learn about the many different steps that your brain has to perform in order to create this simple sense of space. What do I mean by that? Well, let me take you on a brief tour. Just think about what you know right now about where things are. If you were out strolling through the park, you'd be able to see where the pond is, where the duck is swimming. If you listen, you might hear a dog barking or a car going by, and you can probably tell from what direction the dog is barking or where the car is coming from. But your sense of space isn't just about knowing where things are, it's also about knowing what they are. We can identify objects based on their shapes. A coffee mug has a handle on the side and an opening at the top, for example. And you can distinguish between the duck and the coffee mug because their shapes differ. Put another way, the duck doesn't have a handle. We see these things as distinct from each other precisely because we're able to identify their boundaries in space. You can see where the duck ends and the water begins because the pattern of light changes from one place, such as the duck, to another place, such as the water. If you couldn't detect that spatial boundary, you wouldn't be able to tell that the duck and the pond were separate things. And then you'd be surprised when a chunk of what you thought was the pond got up and started quacking. Your understanding of location and boundaries allows you to handle physical objects and move about in the world. You could reach out and pick up the coffee mug, and when you do so, your hands form an appropriate shape to grasp that object. You can walk around the duck pond without getting your feet muddy. You might think that these skills are too ordinary to even be worth mentioning, but nothing could be farther from the truth. A tremendous amount of computational horsepower in your brain goes into accomplishing these very basic tasks. And this class is about how your brain helps you accomplish these seemingly ordinary feats of perception and behavior. It's about how your eyes are like radios, your ears tell time, and how you really do have rocks in your head, very small rocks that help you tell which way is up. It is also about how you know where you are, how you can get from one place to another, and how you might take a shortcut to come back. It's about why it's harder to remember how to get somewhere if you've always been the passenger than if you've driven that way yourself. And it's about why, when you set off to do something and then forget what you were up to, going back to the place where you started might help you remember. In this class, I will talk about how our senses and motor systems work together to construct a sense of space. I'll talk about vision, hearing, touch, body position, movement, and balance. I will explain how your eyes detect electromagnetic radiation, the same kind of energy but in a different range of wavelengths as that detected by radios. Your brain can tell where sounds are by measuring differences in how long it takes for a sound to reach each ear, differences that are less than 1,000th of a second. And those rocks in your head are in the balance organs of your ear. They are tiny little pebbles that slosh around when you shift your position and help you monitor the orientation of your body with respect to gravity. Monitoring our own movements is a critical element of building a sense of space. For example, our sense of where visual stimuli are located incorporates knowledge of where our eyes are looking. But this visual spatial sense has to be updated every time the eyes move, because these movements change the pattern of illumination on the retina. So you have probably updated your sense of visual location many times just in the course of listening to me talk about this one particular topic. You didn't see the world jump because your brain knew it was really your eyes that were moving. So this updating requires your brain to monitor your own movements. When someone else is moving you, such as when you're a passenger in a car, the brain's updating processes don't work as well, and you may have a harder time maintaining your sense of where you've been and where you're going. The story is not just about sensation and movement, but also about deeper aspects of cognition. As the brain constructs a sense of space, it appears to use that sense of space to do more than perceive and move. It seems to use it to help us think and remember. The style of approach in this class stems from my background as a computational and experimental neuroscientist. In my laboratory, my students and I conduct experiments to measure the activity of neurons. As computational neuroscientists, we then try to imagine the different ways that neurons might be arranged to try to figure things out, how those neurons might make deductions about sensory events or signal the muscles about how to move the body in response to those events. This helps us think about how the brain computes, and I'll be telling you about some of those experiments along the way. So this class is about viewing the brain as a kind of biological machine, a device for computing things. If it's about something spatial, it's fair game for this class. Along the way, you'll learn the basics of how neurons work, how they signal information using electricity, and how they communicate with other neurons using synapses. We'll also talk about how real people figured these things out, ranging from the work of ancient Greek philosophers to the experiments conducted in modern neuroscience laboratories such as my own. This course is organized around a book I've written entitled Making Space: How the Brain Knows Where Things Are. So stay tuned. We're going to begin our tour in the next lecture with vision.